want to get set up? Thanks.
So how do you switch? Next and back.
Pretty easy, isn't it? Okay.
Okay.
We're going to try to stay on time and actually go a little bit ahead of time because I think towards the end of the day we're going to start stacking up and having more conversations. So what I'd like to do is introduce Andriy and Vlad here, and I'll let them introduce themselves and where you're from and a little bit about the talk.
Yeah, sure. Hello, are you ready? Yeah, good. Hi everyone, thanks for coming today. So our today's topic is test tooling for 100% of SAI use cases. I'm Andriy Kokhan from PLVision, together with me, Vlad Laslau from Keysight Technologies.
Thank you.
So today we will try to address a few questions. First of all, what SAI use cases we currently have. Also, why we need to improve our SAI testing and the way how we propose to do that. So as you know, switch abstraction interface was initially designed for NPUs. Then it was adopted for external PHY devices, for DPUs. And now we have different combinations of these devices in one box. So you know there is a version of Sonic with external PHY devices. So you have two versions of SAI, SAI for NPU, SAI for external PHY. You can have close in a box where you have multiple NPUs. We can have a smart switch device that runs NPU and multiple DPUs. And as you know, more complicated system becomes, more high probability to face the issues, and it becomes more difficult to catch it and fix it. And we believe that SAI Challenger, which is open source tool available on OCP GitHub, is the way how we can address these issues. And we identified and implemented 3 key pillars for this testing tool. First of all, decoupling of SAI RPC mechanism from the API itself. What it gives us, so we can define the test case once and then use different RPC mechanism to push the SAI configuration onto the device. And a bit later, we will discuss the cases when different RPC mechanism can be beneficial. What is very, very important, traffic generator abstraction. So till now, we usually use PTF, SAI, PTF, snappi utilities to send the packets when we test SAI implementation. But now we are able to run not just software, but also hardware traffic generator on the line rate with the same APIs that we use in our test cases. And also, since our test bed becomes more complicated, and sometimes we may want to test SAI not just in single box, but in kind of topology, we need to have a simple and convenient way how to define or describe this topology. So here the key pillar number 1, how we made an abstraction. So currently we have implementation for 2 types of RPC mechanism. It's a Redis interface and it's a Shrift interface. But due to this pluggable architecture, you can actually define and use your own approach. So in case Shrift interface, you have DUT, you need to put SAI Shrift server into those DUT. Then you can connect through the Shrift API and configure your device. In case of Redis API, you can use syncd daemon from Sonic as a SAI driver. Then you run Redis server on top of that, and you can connect through the Redis way to configure your ASIC. Now, when it comes to the traffic generators, two things. First of all, how we define inside test cases how we will send the packets. And the second one, what types of interfaces and how big, what is the amount of traffic that we want to send, right? So here, few options. We can use still the same PTF SCAPI that we currently, or that we were using till now in SAI test cases. We can use PTF snappi wrapper. It's a Python implementation for Open Traffic Generator. It basically means that you will use the same approach as you used before, but you will be able to send packet at a time on a line rate through the hardware traffic generator. Or you can use directly Open Traffic Generator API for flow-based line rate traffic. Now, from interfaces perspective, it can be virtual testing at CPU speed. It can be physical testing at CPU speed, means you have a NIC on your server and you can connect to your DUT. But also now, it can be physical testing at highest speed and scale. Now I want to pass a word to Vlad to tell a little bit more about hardware testing, traffic testing.
Thanks a lot, Andriy. And I think what is worth mentioning is the syntax that Andriy spoke about is Open Traffic Generator. We come from Keysight. We are the testing company, and more specifically, some of you might have heard about Ixia, the network testing company. And what we want to do, we want to make sure that network testing is available for everyone in all cycles, starting from the software developers, network developers, all the way to the QA teams to the system testing. And for that, we have created a new traffic generator API model. It's called OTG API, Open Traffic Generator. And this is the model, it's open source. The model describes how a traffic generator, how a network tester should behave. And this is based on Open API v3. It's a model that anybody can contribute to, and there are SDKs available in multiple languages. So you can write your network test scripts in Python, in Go, or different languages. It's not test tool specific. It's agnostic to the tool, and it can be implemented by pretty much any tool. And there is a clear separation between the data model of network testing and the actual API, the actual implementation. And I think the biggest advantage is that the same API can be reused across different tools, different type of environments, from software to hardware. So this is the data model that we want to democratize network testing with. We want to make it available for everybody to use. Based on this data model, we also have snappi, which is a client SDK. It's a Python-based client SDK. This is an actual implementation. And if you can see the picture in here, not sure all of you can see it, if you read the script, it's very easy to understand what it does. It specifies how the packets should look like, what's the structure, what kind of testing you are doing. So keep in mind, this is flow-based testing. It has all the power of network testing with complex patterns and complex realistic type of flows, basically. Snappi, as I mentioned, is available for Python. You can easily install with doing pip install snappi, and it has all the beauties, if you will, of a Python SDK. You'll see it once you get to play with it. You'll see how easy it is to write network tests. For more information, it's otg.dev is the website, is the landing page for this new API. And how it actually works, from writing your test script to executing the test script, it starts with the data model first, the data model which is open source, everybody can contribute to. Based on this data model, you have the client SDK. Snappi is a Python SDK. We also have Go, Snappi, or different languages such as Java or C or anything else that you might want to use. And based on the SDK, the network developer would actually write test scripts. Those test scripts are executed against different tools, and the same script, exactly the same script, absolutely no changes. You could run it against a software traffic generator, a container-based traffic generator, or a hardware-based traffic generator from us or from other companies. It's completely portable across anybody who implements Open Traffic Generator APIs. Many of you have heard about Cisco T-Rex as a traffic generator, about XCIX network as a hardware traffic generator, or XCSC is an implementation, a native implementation of OTG, container-based, with quite a bit of power. So from a single CPU core, we can get up to 100 gig of traffic. x86 CPU, 100 gig per core. I think it's very good for most of the network testing needs out there. So this being snappy, I wanted to give you an idea of where we are today on this journey and what is the vision for this open traffic generation. So today, with OTG API, we can do layer 2, layer 3, layer 4 traffic generation, statistics, analysis. And when I say statistics, I'm referring to all the advanced statistics that the traditional test tools provide. Loss, latency, and so on and so forth. Device and protocol emulation, full stateful emulation of a BGP endpoint or an ISIS or SVP link aggregation. So you can also have the traffic generator emulate these protocols. And OTG is already adopted in multiple ecosystems, in multiple open source ecosystems. Some examples, Site Challenger, of course, that Andriy has been describing, but also in Sonic, in Dash, and in OpenConfig feature profiles. So these are some of the ecosystems that are using OTG for network testing. From a platform perspective, it can run in software environments. KNE, Kubernetes Network Emulation, is such a software environment. Container Lab is a different environment, so you can have on your laptop the full environment with test tool and also the network devices, container-based of course, to run the test as a software or network developer. And it can also run on hardware, composable or dedicated hardware. So the vision for this is to have a single test script which can be used against different tools, different vendors, different environments. Starting from generic compute, x86 compute, running the traffic generator on a generic server, at the other end of the spectrum, running the same script, the traffic generator on line rate, dedicated hardware, up to 800 gig of Ethernet traffic generation, and in the middle, something that we call composable compute, using off-the-shelf servers, off-the-shelf switches, and disaggregating control plane and data plane, again, with the same script. And I mentioned in the beginning that we want this to be available for everybody at all stages during the cycle. The XCSC implementation of OTG is free to use, a full-blown traffic generator, free to use, available on GitHub to download, and it has many of the features listed in here. So you can embed it in your workflows and use the simple-to-understand OTG API to drive it as it is today. And speaking about driving XCSC, I'll pass it back over to Andriy to continue the rest of the slides.
Thank you, Vlad. So without going into very details, it's the third key pillars that we identified. It's just a portion of JSON configuration that we use to define our testbed. It's just a sample of what you can do. So here you can see the example how you can define the list of NPUs in your test environment, list of external PHY devices. You define the type of client, which means the type of RPC mechanisms that you are going to use. Here you can see defined Redis interface for NPU, PHY interface for Shrift, IP address, how to connect to the target device, and also data plane. You can see here two sections. One in the top is the type of the data plane is PTF. The second one, the type is snappi. So looks like in one test bed, you can use two different approaches at the same time. Depends on your needs and depends on the type of the test bed that you currently have. So in fact, you can have something like this. So you can have not just one DUT, you can have multiple devices in one topology and multiple ASICs combined together inside one device. And you can use different interfaces to push SAI configuration, Shrift or Redis, or implement your own. And you can use different type of traffic generator approaches to send and receive packets in your network. That's the way how it can be applied. Now we come to the last part of our presentation, use cases. We cannot cover all of them, but we decided to highlight just few. I would call it frequently asked questions. Use case number 1, you know that there are many already available SAI test cases in the community provided by community, mostly focused on single NPU. Now you can use SAI Challenger as an umbrella for those PTF test cases. You describe Testbed inside JSON. The SAI Challenger will translate JSON into PTF configuration, and with 0 changes, you can execute existing SAI test cases. Use case number 2, self-contained DUT. We heard a few times the questions whether this test framework can be run inside single physical or virtual device. Since SAI Challenger is designed to be inside Docker container, so it's very easy to deploy it and use it for virtual testing or physical device testing. In such case, it will be using as a virtual network inside this virtual testbed, or probably your device contains a way to send the packet somehow from CPU to the beginning of the pipeline and capture at the end of the pipeline. So that's possible, use case number 2. Probably my favorite one. Its favorite, if you have Sonic devices and at some point you will realize that you face some issue and you suspect that it can be SDK or SAI related issue. You don't need to build some extra applications. You don't need to waste your time to deploy this extra application to the target device. You just power on your Sonic device, you start SAI Challenger, it connects through the SSH to your box, stop all the services, and here is the benefit of the Redis interface that you can use in your test cases. Because you just use the same Redis database Docker container, you use the same syncd container that is available in Sonic, so you basically deploy nothing to your running device. And of course, SAI Challenger provides a simple and convenient SAI CLI that you can use to remotely do some manual stuff to check some attributes and so on. And the last one for today is a Sonic chassis case. SAI Challenger sees Sonic chassis as a multi-DUT topology. So inside Sonic chassis, you have supervisor card. You can have multiple line cards. Each of them is designed as a separate Sonic device. So basically, it's the same case as I was showing before, just scaled into kind of multi-DUT topology. So the same way SAI Challenger connects, stops services on those devices, and run the test cases. That's all for use cases. Call to action. As I mentioned, it's open source. It's available on Open Compute Project GitHub. It's very easy to use because it already contains a simulator that you can run on your PC. So it's easy to try it, to start using it. You can scale to the line rate, as Vlad described before. And one interesting part that is currently available on the GitHub, Chris from Keysight contributed a very good document that describes different use cases, how you can use SAI Challenger together with OTG. So I suggest you to check this. If you see something is missing or you have your own use case, you can message to us and we will try to help you. Thank you very much. Probably some final questions because we already run out of time.
Thank you both. Thanks, Andriy. Thanks, Vlad. Any questions? And again, we have the microphone in the back, or you can just kind of shout out and we can. Yes?
Yeah, what about PTF tests?
If you don't mind repeating the question.
Yes. The question was, what about PTF tests? As I mentioned, we have use case number 1. We can use SAI Challenger as an umbrella. Cool thing is that you don't need to modify existing test cases. I tell you even more, you can try to write the test cases inside SAI Challenger the same way using the same API that you have in your PTF environment, but I wouldn't suggest doing this because you will stick to the Shrift RPC mechanism. So the suggestion is use the way to define the test cases that were provided as a part of SAI Challenger development.
Thanks. Follow-up question? Okay, good, thanks. Other questions? So I have one. I noticed that you've already done some integration with Sonic. Are there other operating systems that you're considering that could be integrated?
Yeah, so I believe at some point Dent will be there. I mean, probably SAI available in Dent, right? So since we focused just on C# abstraction interface, obviously you can use it for testing SAI in different environments, not just Sonic. Also, I believe that can be interesting for FBOSS users because it's not just about different hardware, it's also about the type of applications that is running on top of SAI and the way how this application is using SAI, right? So that's, I believe SAI Challenger is the right way to go here.
Thanks.
Sure.
Thanks. Any other questions? Okay, we have 5 seconds. Okay. Well, thank you very much. Really appreciate both of you joining us today.